humanity has always reached for the unknown, from our own planet to the cosmos surrounding us. As that reach is going further than ever before, we turn our attention inward to a mighty group of creatives at the Goddard Space Flight Center. These powerful creatives tell tales of the earliest days of the universe and far beyond. We bring you now into their world. Welcome to the Goddard Film Fest.
Artemis is our 21st century return to the moon. Together, NASA, international space agencies, and a growing global space industry will explore Earth's nearest neighbor with advanced robotics and our next generation of astronauts. But where will our astronauts explore? The moon is a treasure trove of scientific discovery, and NASA has its sights set on the South Pole. This mysterious region features soaring mountains and deep craters, leading to unique locations that experience nearly continuous sunlight, in contrast to nearby depressions that never see the sun. Artemis 3 will mark humanity's return to the lunar surface for the first time since 1972. NASA has identified 13 regions near the South Pole that meet safety requirements for landing and present opportunities to search for lunar resources. Each region can also help us learn more about the history of the moon and gain a better understanding of our place in the solar system. These 13 candidate landing regions represent a diversity of features in the lunar South Pole, ranging from the summits of mountains rising miles above their surroundings to the rims of large craters. These features together act to both expose and preserve billions of years of geologic history. Using robotic orbiters and rovers, NASA and the global science community will continue to study these regions before selecting the Artemis 3 landing site. The astronauts selected for this bold expedition will literally and figuratively shine a light on some of the deepest, darkest areas of the solar system, revealing ancient secrets of the universe.
There is one place where we're seeing climate change unfold faster than anywhere else on Earth. Here. In fact, temperatures in the Arctic and boreal regions are rising nearly 4 times as fast as those in the mid-latitudes. That's why NASA has teamed up with local partners to better understand the vulnerability and resilience of these ecosystems, while also gathering valuable data that will help future Earth-observing satellites. From space, air, and on the ground, we'll see how scientists are piecing together the story of the Arctic, from how it is changing to what that means for our planet. Because as they say, what happens in the Arctic doesn't stay in the Arctic.
PPA is engaged. And we're radiating.
One of the best ways to track how an environment is changing is to observe it from above. But where weather and vegetation can make it difficult to see the ground with the naked eye, specialized radar can pierce the clouds to give us a crystal clear look at the landscape. This special device, weighing nearly 1,000 pounds, collects data about soil moisture, vegetation, permafrost, and other environmental processes on the ground below. In fact, it's so precise that NASA developed a special system for pilots to fly the exact same flight path year after year to get an accurate reading as to how a landscape is changing over time.
So with the airborne data, we can target exactly where we want to go and exactly when we want to go there, and we get very high resolution data, so we can have a really clear picture of what's on the ground.
That's Dr. Liz Hoy, senior scientist for NASA's ABOVE mission. ABOVE has spent the last 7 years studying environmental changes in the Arctic and boreal regions. The mission uses satellite, airborne, and ground data to get a complete picture of what is unfolding in these ecosystems.
So our satellite data gives us a very broad picture of what's happening all over the landscape. And then with our airborne data, we can target specific locations and times when we want to get imagery. And then we can compare both our satellite and our airborne data with what's happening on the ground when we have teams actually out on the ground making measurements. And putting all that together is really where we get a lot of the power of what we're able to study.
NASA White Sands is a remote test facility that the agency uses for some of the more dangerous testing that is needed to support the NASA missions.
The size of the guns, the biggest gun we have is about 225 feet, and the building itself is only about 200 feet long, so part of the gun does actually stick out of the building.
There is a very, very large project underway right now that started not too long ago with the landing of the Perseverance rover on Mars.
I am a system engineer for the capture, containment, and return system. This system is the NASA payload, which is basically responsible to bring the samples, the Mars samples, back to Earth.
What I'm standing in is actually called a hypervelocity test facility. It's where we shoot little projectiles at objects basically as fast as we can achieve on Earth. In our case, we are testing to see what will happen to our designs if they were to be impacted by a micrometeoroid on the trip to or from Mars. The goal here is to see how well those materials withstand those impacts to make sure that we don't lose containment of our sample.
Hypervelocity guns work in two sections, which are a two-stage light gas gun. We pressurize hydrogen in the first section. In the middle of the gun, there's a barrel. That's where the projectile is held. The pressures that are generated from these guns can actually level the building. And that pressure is suddenly released where the projectile is, where the barrel in the middle of the gun is. And then from that point on, there's a simulated vacuum, which simulates space. And then it is impacted where the target is.
It's all about the timing. You're dealing with about 500 microseconds. Where's the time of the event?
So unlike a traditional firearm, a lot goes into preparing these guns for a shot. Setup takes anywhere from an hour to a full day. Gunpowder is prepared and loaded by hand.
We're able to remotely operate the guns via the bunker. On the count of 3, 3, 2, 1. It's equal to 25 times faster than a .44 mag. The velocities are also like flying from New York to San Francisco in 5 minutes.
One of the interesting things that we learn is that a massive piece of metal does not offer the same level of protection of really thin pieces of metal, but stack all together. What we're doing is we have very light layers of material, and those layers, they function to progressively break the particles until the very last layer that just receives all the energy from the hit, and it stops right there.
If it wasn't for this study, we would be sending up rockets and satellites and pieces of the space station not knowing whether they were going to protect the astronauts or the equipment we send up.
It's a really neat thing to see when you test something and have it correlate very well back to your simulations. I am super excited to be working this mission to bring back samples from Mars. It is something that has never been done before.
And we are learning so much from this, especially because it's Mars. It's a planet that we had fascinations for a very, very long time. So it is humbling and a lot of work, right? Being here, testing things, it's amazing.
If you want to make a spacecraft, you've got to break a few eggs. No, that's not right. You've got to bake for a few days. That's it. So follow along for our recipe for homemade satellite. First up, collect your ingredients. We're making an ocean, land, and atmosphere monitoring satellite called PACE. So we'll gather 2 polarimeters, which measure the polarization state of light as it travels through water and atmospheric aerosols, and 1 ocean color instrument, which will measure light reflected from the ocean surface to study tiny ocean creatures called phytoplankton, as well as atmospheric properties above the ocean. Wrap these individual components in special spacecraft foil. These blankets for satellites help keep the instruments that need to be hot, hot, and those that need to be cold, cold, while they're in space. We make them special right here at Goddard. Place the instruments in the thermal vacuum chamber, or TVAC. This chamber mimics some of the extremes the satellite will experience. Space can be very cold, but sunlight can heat the spacecraft up. This test ensures the spacecraft and its instruments will handle both. It also creates a vacuum, like the vacuum of space, to make sure the satellite can withstand those pressures. We'll bake the satellite components at a variety of temperatures and pressures for several days. When your timer goes off, remove PACE from TVAC. It's time for the last step of building the spacecraft, assembly. We'll install PACE's instruments to get ready for launch in 2024 and a new view of our home planet's ocean and atmosphere.
Artemis 1, the first test flight for the Space Launch System mega rocket and the Orion spacecraft. On board is Commander Muniken Campos, a mannequin wearing a next-generation spacesuit called the Orion Crew Survival System. Muniken Campos is outfitted with sensors that will provide data to help protect astronauts on future Artemis missions. But why is this mannequin called Muniken Campos? The mannequin is named after Mexican-American electrical engineer Arturo Campos, a key player in the Apollo 13 astronauts' safe return to Earth. It was April 13, 1970, when Campos got a phone call in the middle of the night.
Okay, Houston, we've had a problem here.
It was night. We got a phone call, or Dad got a phone call. We heard our parents talking, so we went downstairs. Y preguntamos a mi mamá qué estaba pasando. Y dije que la NASA habló y estaban teniendo problemas con la cohete.
That's the day that my dad saved the astronauts.
When Campos arrived at the Space Center in Houston, he learned that an oxygen tank in the Apollo 13 service module had ruptured. The service module's normal supply of electricity, light, and water had been lost, leaving astronauts Jim Lovell, Jack Swigert, and Fred Hayes stuck in a damaged spacecraft about 200,000 miles away from Earth. The main challenge was to find a way to divert enough power from the lunar module to the command and service module's equipment system so that the astronauts could safely return to Earth. Fortunately, Campos had already written this procedure, since he dreamed about it a year earlier. Campos, born in Laredo, Texas in 1943, showed an early interest in tinkering.
He was a mechanic by nature.
Yeah.
He worked on automobiles.
His father taught at the college auto mechanics, and so he learned mechanicking from his father. He received a grant to go to the University of Texas in Austin.
Eventually, Campos graduated from the University of Texas in electrical engineering and began working for NASA in the early 1960s, becoming one of the people in charge of the electrical systems in the Apollo program. When the problem surfaced during the Apollo 13 mission, Campos immediately began reconstructing his plan to provide sufficient power to the command module.
He came up with the solution to give the batteries enough power to get those astronauts back here.
And so they used it, and thank God it got them back home.
Campos and other members of the Apollo 13 mission received the Presidential Medal of Freedom in 1970.
This means a whole lot. The President of the United States signed it. Not a lot of civilians got it, and my dad did. And we couldn't be any prouder of Dad. We could not be any prouder of my father.
Campos passed away in 2001 at age 66. And his name has left an everlasting mark at NASA.
Very proud of my dad.
Absolutely. Apollo 13 is his legacy. Estamos muy orgullosas.
And we have liftoff of NASA's Mars Global Surveyor as America begins its journey back to the red planet.
6 solids burning.
And when Mars Global Surveyor started getting closer to Mars, we were going to go into this aerobraking phase. That was an opportunity that we had to go ahead and turn on the lasers and see if we could track the surface.
Somebody being carried it for him.
And Station 45 was having problems locking up to the 2K data.
What was that?
You said 1607 or 16...
Can you tell if the MOLA has been turned off?
Copy, I'll try to kill my query and restart it as soon as that query is up
That
and
the
running.
native event? That must be the native event.
I'm hungry. I didn't really want those sandwiches.
Look at the laser coming back, Rob.
Greg says about 1840.
It's going to be too fast and I got too much data coming in. Look, there's a little tiny terrace. This is the first profile of a crater we've ever seen on the planet. Rob, nice laser. We have Mars, finally. 12 years. All right, let's take a look. I don't understand.
Over a decade later, the Goddard team had proof. planet-scale laser altimetry worked. It could map distant craters and valleys and mountains. It changed the game.
Today we've ushered in a new era in the remote sensing of Mars.
And this particular data set that we've acquired has in fact enabled us to generate what we consider a very detailed description of the shape of the planet Mars.
This has significant implications for the flow of water early on Mars.
We believe this is one of the youngest features on the planet. We're seeing a planet that is very different from Earth. And it's telling us something about the Earth in an indirect way that says that not everything works in the way that we originally had in mind.
The kind of measurements that we're making now are allowing us to, characterize Mars on timescales of days to years now. And then the next step is to try to go back eons and try to figure out what changed on Mars.
I mean, at that time, we used to brag that Mars was mapped better than the Earth. The accuracy of MOLD was so good, and after a couple of years, the coverage was so good. It was definitely a more accurate map of a planet than any planet.
And this came out of it can't be done in the mid-'80s to a tool that we now accept as the standard.
For those of us that worked on MOLA, it was transformative. It wasn't at a destination or a place that we were as much as a place that we would become.
It's 900 degrees hot at the surface, has powerful high-altitude winds, and is blanketed by a dense carbon dioxide atmosphere. The planet Venus. Although the same size and density as Earth, the similarities end there. Earth has water and light. Venus is desolate, dry, apparently lifeless.
The Da Vinci mission, named after Leonardo da Vinci, will now take us back to Venus and address unresolved questions about this mysterious planet. This exciting new mission will launch in June 2029. During 2 gravity-assist flybys, Da Vinci will study the cloud tops in ultraviolet light, tracking cloud motions and analyzing mysterious ultraviolet-absorbing chemicals. Both flybys will also examine night-side heat emanating from the surface. These geological clues will paint a global picture of surface composition and its evolution. 7 months after our second flyby, Da Vinci will release its atmospheric descent probe, which will enter the atmosphere over the course of 2 days. The probe will take about an hour to fall through the atmosphere, taking measurements down to the surface. These measurements will include profiles of composition, winds, temperature, pressure, and acceleration. Key gases will help us understand how Venus formed and evolved. Some of these measurements may even reveal signatures of ancient water. The spherical probe houses the state-of-the-art instruments that will work together to address questions about the Venus atmosphere, protecting them from the extreme temperatures, high pressures, and acidic clouds in the environment. Da Vinci's camera peers down through a small viewing port, and once the probe passes below the clouds, it will start to collect a series of 3-dimensional views that will also help us understand whether the rocks of the Alfa Regio Highland region reveal a story of an ancient continent shaped by water. And an oxygen-sensing student collaboration experiment will reveal the role of this gas in the deep atmosphere. The discoveries that emerge from this diverse data set will help tell us whether Venus was once habitable. And the story that we reveal will reach even beyond our solar system to analog exoplanets that will be observed with the James Webb Space Telescope. Venus is waiting for us all, and Da Vinci is ready to take us there and ignite a new Venus Renaissance.
In 1972, the first Landsat satellite was launched into orbit, ushering in a revolutionary new era of Earth observation. More than 50 years and 8 satellites later, the Landsat program has collected an immense amount of data that's proven an invaluable resource to scientists studying the complexities of our planet's surface. The abundance of data provides insights, but it can also pose a daunting challenge for researchers to extract and analyze information. Landsats 8 and 9 alone each gather close to a terabyte of data per day. Enter artificial intelligence. AI's popularity has taken off in recent years, with new tools that allow users to generate imagery, transcribe audio, and even compose music at the click of a button. This is nothing new for the scientific community, however, which have been using artificial intelligence methods for decades. When it comes to working with Landsat data, one of the most popular AI tools is machine learning. Machine learning is a subset of AI that can train computer programs to recognize patterns and analyze imagery, skills that prove exceptionally useful in the application of Landsat data. In fact, when combined with Landsat, machine learning models have led to a number of advances across a variety of scientific fields, granting further insight into our planet's past, present, and future. One of the major challenges of working with satellite imagery like Landsat can actually be found up in the sky. Clouds. Obscuring Earth's surface and casting shadows that reduce visibility, a cloudy day can be a downright nuisance when it comes to analyzing certain satellite imagery. Pinpointing these clouds helps to improve data quality by removing noise and artifacts, making it easier to detect changes over time. But while accurate cloud detection across a massive dataset such as Landsat's would be a tall task for any one human, it's a piece of cake for a computer. In 2019, researchers from Oregon State University constructed a deep convolutional neural network model, a machine learning tool that excels at recognizing patterns in imagery. With the help of existing Landsat 8 data, they taught their neural network to automatically detect clouds in satellite imagery with an amazing 97.1% accuracy rate. The researchers believe in the future, cloud detection algorithms like this one could even be harnessed to identify clouds across the entire Landsat 8 archive. Machine learning's benefits don't just end when the clouds clear. Down on the ground, there's plenty to keep an eye on. Our planet's one constant is change. Earth's surface is perpetually evolving due to human and natural forces. Landsat's ability to track these changes over time has proven to be an incredible asset to the scientific community, especially when used in concert with machine learning. For example, researchers from the University of Texas at Austin used Landsat data with a random forest classifier, yet another type of machine learning tool that combines multiple decision trees to make predictions. Using data from Landsats 4 through 8, they used the classifier to map changes in land use in northwestern Belize from the 1980s to the present. The results showed that tropical forests and wetlands that don't have a designated protection status are increasingly vulnerable to deforestation due to Belize's expanding industrial agriculture. By combining these new advances in machine learning with Landsat's capacity for looking back in time, researchers believe in the future, this approach would make it possible to provide robust estimates of deforestation in Belize. As climate change drives our planet's temperatures higher, so does the prevalence of extreme events that put ecosystems at risk. Wildfires across the globe have increased in frequency and intensity. Australia is no stranger to these types of fires. The 2019-2020 bushfire season was one of the most destructive on record. Using satellite imagery to pinpoint when and where wildfires are burning can be an important tool for assessing damage in future fires. Researchers at the University of Western Australia developed a new machine learning approach with the help of Landsat 8 data to generate a 16-year history of wildfire severity in the eucalyptus forests of the continent's southwest. They fed data gathered by satellites, including Landsat 8 in 2005 to 2020, into a supervised classifier, a type of machine learning algorithm that learns to classify data based on labeled examples provided during training. By teaching the algorithm with examples from the past, this method of machine learning could be used to predict the severity of future wildfires, critical data that could aid in the management and conservation of Australia's extensive eucalyptus forests. These are just a few examples of the remarkable ways Landsat data and machine learning tools are unlocking new possibilities for understanding our planet. This combination has already led to significant advances in agriculture, forestry, urban planning, climate change research, and more. As more satellite data becomes available and machine learning techniques continue to improve, so too will the potential for applications in additional fields critical to the health of our planet's ecosystems. In tackling the complex challenges of today and tomorrow, the blending of Landsat data and machine learning will be vital to help people make better decisions to protect our planet.
One of Earth's closest neighbors is a dark, jumbled mass of rocks and boulders known as asteroid Bennu. Bennu is ancient, a rugged survivor of the solar system's chaotic past that may hold clues to the origins of life. In October 2020, a NASA spacecraft called OSIRIS-REx touched down on Bennu and collected a sample for return to Earth. Scientists had expected that this touch-and-go event, or TAG, would have little impact on the asteroid. After a slow descent, the sampler head would briefly make contact, inject a puff of gas, and capture a handful of material. Perhaps it would also leave a small divot at the sample site, a subtle footprint in the soil, or so it was thought. When images of the TAG event beamed back to Earth, they were far more dramatic than anticipated. Despite its slow touchdown, OSIRIS-REx had punched through the surface and set off an explosion of loose material. Tons of rocks and pebbles were ejected, radiating outward in a wall of debris. The pictures were stunning, but why did Bennu's surface behave so unexpectedly? The answer involves cohesion, an attractive force that can bind molecules together. Cohesion gives water its surface tension and keeps droplets together even in a microgravity environment like the International Space Station. Granular materials like wheat flour, cocoa, and dust can also exhibit cohesion, which pulls individual grains into clumps. On Bennu, scientists had expected cohesion to act like a bit of glue between the rocks, making its loose surface more solid. But the TAG event showed that Bennu's uppermost layers are nearly cohesionless, deforming under stress like a fluid. A good analogy is a ball pit. Although the plastic balls are solid, they easily slide past one another and past boisterous children, behaving in mass like a fluid. Thanks to OSIRIS-REx, we now know that Bennu's surface is not held together by cohesion, but by gravity, or microgravity, with a minute tug less than 100,000th the pull of Earth. On the Moon, gravity is 16% as strong as it is on Earth, and more than 16,000 times stronger than it is on Bennu. As a result, loose material in the lunar subsurface is packed together more tightly, making the Moon's surface relatively firm. If a 50-kilogram mass of solid iron were to hit the Moon at the same speed as the TAG event, it would sink into the ground by only half a centimeter. Repeating this experiment at Bennu would yield a dramatically different result. Though the mass would strike with the same force, it would plunge 17 centimeters before stopping, over 30 times deeper than at the Moon. Bennu has consistently defied scientists' expectations, as each new finding reveals another facet of this small but surprising world. Using data from OSIRIS-REx, we now have the ability to look back and accurately recreate 30 seconds on asteroid Bennu. On October 20th, 2020, OSIRIS-REx made its final descent to a sample site called Nightingale. With its TAG-SAM arm outstretched, it approached the surface at 10 centimeters per second, the walking pace of an insect. 1 second after contact, it released a canister of pressurized nitrogen, detonating an explosion of particles and driving material into the TAG-SAM head for sample collection. 6 seconds after contact, while it was still sinking into Bennu, OSIRIS-REx fired its thrusters to begin the back-away maneuver. The engine burn lasted for 24 seconds, continuously pushing against the spacecraft and rapidly slowing its descent. Flying debris from the thrusters and the gas release pelted the science instruments, clogging them with dust. 9 seconds after contact, when OSIRIS-REx had sunk nearly half a meter into Bennu, it reversed course and began to rise. At 16 seconds, the TAG-SAM head re-emerged from the subsurface as the spacecraft continued to accelerate. 30 seconds after contact, OSIRIS-REx shut off its thrusters and drifted away with its sample of Bennu. Almost 6 months later, on April 7, 2021, the spacecraft returned for one last flyover to observe its footprint. At the point of impact was a new crater, averaging 8 meters across and reaching 68 centimeters in depth. Thruster marks overlapped with this TAG crater in an X pattern, increasing its volume by as much as 40%. A ridge of ejected material that had been kicked up during sample collection and then fallen back to the surface circled the crater like a campfire ring. With a puff of gas and an engine burn, OSIRIS-REx had displaced 12 cubic meters of granular material, 6 tons of loose rock that may have been packed together as lightly as a bowl of popcorn. After a final departure maneuver in May 2021, OSIRIS-REx began a 2-year journey back to Earth. Stowed on board were about 250 grams of asteroid Bennu, a bounty of scientific treasure destined for future discoveries.
We're here in Australia, and we're gonna launch some rockets. We're following 2 teams of scientists here to study a special pair of stars we can't see from most parts of the US. They're part of the Alpha Centauri system, the closest stars to us besides the sun. And with the help of NASA sounding rockets, they'll capture light from those stars that doesn't reach the ground and propel humanity's search for habitable worlds into the future. Yes! Follow along as I go into the outback to show you what it takes to launch a rocket and make groundbreaking scientific measurements. There's a rocket in there.
3, 2, 1.
Hang on tight. We're going on an adventure, high above, down under. Today, it continues to drive photosynthesis, light our way, and keep us warm. I'm Miles Hatfield, and in this episode, we're talking about living with a star. We've been putting together this video series called High Above, Down Under that's all about us following this two rocket teams to Australia, where they were going to be the first launches from a brand new launch range. And we talk about the science they were doing, but we also wanted to capture the experience of what is it like to be in the field.
So Miles and I are both writers, which means this was kind of our first time really delving into the videography side of stuff, which was a huge, challenging and very rewarding learning curve.
One of the cool things about sounding rockets is that, they launch up and do their science up in space, and then they fall back down. And so you got to go recover the parts. So you can see a little bit of us going out to do some of the recovery. Looks pretty expired to me. We wanted to have a lot of fun. We wanted that to come across in the video. Earth is packed with life. Earth is packed with life. Earth is packed with life. Like and subscribe. Is Earth packed with life? Comment below. Earth is packed with life. Earth is packed with life. Earth is packed with life. Ah, there's some life biting me right now. Why are you smiling? Because you're about to fly. We had a great time out in the field recording all this video. Miles is out there getting bitten by ants while we're recording, and there's spiders everywhere. That's just a terror.
That's huge. Southern Hemisphere target speed.
But we're also getting to talk with and hang out with all these amazing people, from the engineers to the scientists to the people who helped make the rocket range, and all the local rangers who know all about the flora and fauna and all the local history as well. It was a lot of fun filming this series, and we hope you guys will enjoy it too.
The spacecraft and instruments are all together assembled in this chamber behind me, and we are blasting them with acoustic energy to look at the response of the different parts of the observatory and make sure nothing gets damaged. And the reason we do this is to simulate the launch environment for the vibration in the acoustic range during launch. Today, the full level that we get up to is almost 140 decibels, which is very loud. It would definitely damage your hearing. It's like the same kind of noise you'd hear if you were close to an airplane with a jet engine or a very loud rock concert near the speakers. For years, I've been witnessing tests in this chamber for various missions, and I always see the large speakers in there. And they're shaped like cones, which remind me of bells of brass instruments. And so I thought, what could we do to have a group of musicians play and see if they could equal the sound that we simulate during one of our launch acoustics tests.
On January 15, 2022, the uninhabited volcanic island Hungatonga Hungahape erupted violently, creating worldwide shockwaves, sonic booms, tsunamis, and powerful winds, all while blanketing surrounding islands in 2 centimeters of ash. It was a fatal eruption, and its impact on nearby communities was further compounded by the disruption caused to emergency services. NASA has been following the Pacific Islands' unusual evolution for years. Using historical observations and satellite data of the January eruption, scientists have shed a new light on why this explosion is so unique and how such a small island is making such a huge impact across the planet.
It gave us a window into a rapid-paced life history of an island that we can compare to hundreds of other islands in the oceans over time. And these islands are sensitive indicators for the activities of climate, environmental change, and we can project them forward even to other planets. So what an opportunity.
Geologic records suggest that while the volcano may have produced massive explosive eruptions in the past, an eruption of this magnitude wasn't expected so soon.
This was what we call a volcanic explosivity index 6 eruption. Nothing like it since Krakatoa in the 19th century. And so what happened was this beautiful little island, 100 meters tall, growing, forming by the nature of the way volcanoes and water interact, was explosively changed forever. And literally the entire base of the volcano fell hundreds of meters into a shallow magma reservoir, a liquid rock chamber, literally under the ocean. And that allowed the explosive interaction of a massive Pacific Ocean seawater with this hot rock, 1300 degrees Kelvin. That's super hot, hotter than your oven. And that explosion with the pressure moved the water, the rock, the small amounts of ash that were part of building the island all the way into the atmosphere and triggered a large tsunami, a 15-meter high superwave that traveled out hundreds of miles, buried some local islands as part of the Tonga archipelago, but allowed us to see the power of Mother Nature's volcanoes when water and liquid rock come together to shape our planet.
NASA and ESA satellites clocked wind speeds up to 450 miles per hour, just hours after the eruption, and showed material rising up to 36 miles, the highest volcanic plume ever measured. Within 2 weeks, the main plume of volcanic material circled the entire globe, injecting dust particles into the stratosphere that remained for upwards of a year. NASA also found that the volcano injected a tremendous amount of water vapor into the Earth's stratosphere. The increase of water vapor, which traps heat, could modify atmospheric chemistry and have a warming effect on the Earth's surface. So outside of its sheer magnitude, what makes this eruption so unique? Well, it's really a matter of our ability to see it. At the end of 2021, the island's volcanic activity started picking up. Small underwater eruptions began to reshape the island's landscape, expanding the island. These shallow water events are classified as Surtsean eruptions, where hot magma interacts explosively with water. In other words, we've been able to see the birth of the island happen in ways we haven't been able to before. And with modern satellite technology, we're also able to see the end of the island's life cycle in new detail, as we did with the January eruption.
This has happened in Earth history, in famous places like Yellowstone, Taupo, New Zealand, Krakatoa, and now in the island nation of Tonga. And so we have an opportunity, 21st century techniques, laser altimeters like ISAT-2, satellite techniques that can see at scales of sub-meter, put those together and tell a story of the birth and death of this island.
NASA's vantage point of Hunga Tonga Hunga Hape could even be used as a means to study other planets in our solar system, specifically the role that volcanic islands play in water planets like Mars and Venus.
We live on an ocean planet, and so these kind of eruptions are part of our history, how we got here as we evolved ourselves in the context of our planet. And we want to take the lessons that we learn as we go forward, as we continue to watch what's next in this exciting volcano, and apply it forward to other worlds, like Mars and Venus, that may have harbored surface waters as oceans or seas, and understand them in the context of our Earth.
Using geostationary satellites and observed data, NASA's scientists hope to learn from the continuous evolution of this special volcano.
The question is, will those come again at Hunga Tonga and then explode again? We don't know. So we need to use what we saw from this eruption in 22 to train ourselves for what to be able to predict. And so this is our chance to learn and then to apply it to the other ocean worlds nearby that we really hunger to study.
Looking for a new vacation spot? I've heard that gamma ray bursts are beautiful this time of year. No, oh, no, I was just, no, they're far too dangerous. With deadly gamma radiation? So you're really going to go? Then you need to know a few things first. A gamma ray burst is a giant burst of gamma rays, the highest energy form of light. They mostly come from either two neutron stars crashing together or a massive star collapsing in on itself. Both likely form black holes that blast out a pair of cones of super fast, super hot material. These jets emit the gamma rays that give gamma ray bursts their name. If you're in the path of that cone, even very, very far away, you see a gamma ray burst. Not in the cone, no gamma ray burst. But the show isn't over yet. As that cone rams into the stuff around it, there's another display across the whole range of light, from radio waves to gamma rays. Well, and there's other possible light shows too. The supernova from the collapsing star, or the kilonova from the merger. You get the idea. It's a brilliant display. Now, gamma ray bursts may be the brightest show in town, but knowing when and where to look can be tricky. Over at Earth, they're also known as Glurbax 29D, depending on where you're from. Gamma ray detectors monitor the whole sky to find these unpredictable events. But if you want to visit one, you'll need to find it before that blast of gamma rays. First, you need to decide which type you want to see. The initial burst from the crashing stars lasts just a couple of seconds or less, while the collapsing star can have a burst lasting minutes. But timing your visit to the collapsing star might be a problem, unless you're willing to wait. A long time. Like really long. We know of quite a few stars that could collapse soon, but that could mean a day, a year, a million years, or more. Predicting when the stars will crash is a bit easier if you're willing to do a little homework. Just find a close pair of orbiting neutron stars, watch them for a few orbits, add some math, and you can predict when they'll crash. Now, before you run off, make sure you have what you need to keep yourself from getting blasted by those gamma rays. Earth, Glurbax 29D, has an atmosphere that shields the planet and its inhabitants from gamma rays. And you'll need to be able to detect light in all its forms if you want to see the full show. Of course, all of this doesn't account for the fact that gamma ray bursts don't happen nearby. The closest so far was over 100 million light years away, and most are billions. So you'll need to find a galaxy where this is more likely. But it looks like you've worked all of that out. So keep in mind these tips and tricks, and go enjoy the universe's most spectacular fireworks display. Ugh.
Sprites, I saw them on a documentary once, and I kind of became fascinated with them. I've been trying to capture them for a while, so it's kind of all snowballed into a semi-obsession.
Whoa! Whoa! I saw that one too.
I saw that one.
You saw that red one?
Yeah.
I can't wait to look at that one again.
My name's Paul Smith, and I'm a sprite chaser, which means I like to photograph the night sky and sprites in particular. They look like, to the naked eye, you would probably see them as flashes above thunderstorms, and then the camera picks up more of the colors. Nice red, orange, sometimes purple colors.
I would say the region of space about the thunderstorms is almost like an electrical zoo. We have these collection of electrical activity. We have blue jets, gigantic jets, trolls, halos. It's almost like an electric fairy tale. Sprites is just one of many. Collectively, we call these transient luminous events. Sprites are like snowflakes. They come in various shapes and sizes, so we call them angel sprites, carrot sprites, column sprites. They're just beautiful to look at, and just the fact that no sprite is identical to the other is good enough reason to study them and look at them all day long. You're never going to get bored. So sprites are very large-scale events. Their width is usually up to 5 to 10 kilometers, and their vertical extent is about 40 or 50 kilometers. You can almost fit a small town in there. Because these sprites are very large-scale events, they change the atmospheric composition, and we don't know the extent of this effect. So it's important to study them in the long run.
It's just a real cool thing to be able to shoot and see these things that nobody else is really getting on a regular basis.
I saw their phenomenal images and I wanted to work with them and leverage their images and data collection. And it sparked this idea in my head, what if I created a citizen science project that I can connect the public with the scientific community so we can further our understanding together. With this new citizen science project, our goal is to create the first ever comprehensive database of sprites. I'm very excited about this. I know there are a lot of people out there who are naturally chasing sprites, so I'm asking all sprite chasers to submit their images to us. It's like a puzzle. They provide one piece, we provide the other, and we solve it together.
With this citizen science project, I'm just really excited to think that finally we'll have a connection, because I've been getting these sprites for so long and I got a bunch sitting on my hard drive that nobody's really dissected or looked at. So I think this will be a good bridge for that. So there's a chance for storms and sprites, so let's get to it.
I have been studying sprites for 15 years and I have not seen them in person. I am super excited about the opportunity to go chasing with Paul. I haven't met him before and I'm going to be meeting him soon, so we're going to go capture some sprites.
Hello.
Hi, Paul. Hi. It's so nice to meet you. How are you?
You too. I'm doing great. Awesome.
Let's have a fist bump. So, what's our plan today? Where are we heading?
Well, we got some storms over in Arkansas and Mississippi that will be in range if we head down to southeast Oklahoma.
Okay, let's go sprite chasing.
Let's go. So the best places to catch sprites are where you've got big lightning strikes. We're heading to a lake in a dark sky area of southeast Oklahoma.
So when you look at the radar, we are mostly looking for those regions that have red cells, and the system was evolving to be able to form some powerful flashes, which we need for the sprites tonight. So it's looking good. Hey Paul, so what other tips you have for sprite chasing?
I always try to look for really dark skies. Maybe at first look on Google Maps and just find areas without any development nearby.
In a quarter mile, keep left at the fork. Follow signs for Daisy.
Okay, yeah, it looks pretty open here.
Yeah, that's the direction we're looking. So.
Right, perfect.
Where the storm was on the map, I just lined us up on Google Earth to like a landmark. I could see this point of the bridge here.
So yeah, we are right now here in Oklahoma, but the storm we are looking at is over Mississippi-Alabama state border, and that's pretty far out. We are talking about 375 miles, so it's pretty far out. When I look at the screen, I'm pretty much scanning the horizon here because the storms are pretty far out, and I'll be able to just see the lightning flash the top or the cloud tops, pretty much that light, and then that's my clue to trigger. And that's when I press the button, and I don't see the sprite until I actually replay that little capture. And I'm hoping that I actually captured something.
I mean, I'm kind of thinking, because if I don't see something, oh, there was a sprite.
Seriously? And then the moment I just turned my head, seriously?
There was a sprite, guys, yeah.
Let's see.
I hope I caught it in
Oh
time.
my gosh. Yes! We had one. Oh my God, that's awesome. And that was actually pretty close.
Pretty close.
High fives, high fives. We did it. Oh. Perfect! I think we got one. Awesome. And I think that was a column sprite. It's right there. We actually captured sprites. I keep replaying this. This is amazing. Yeah, that's why now I understand why you don't want to leave. Once you have one capture, this is all what science is about. It's just this excitement and trying to understand how they're formed and what makes them look the way they are. It's just amazing and a highlight of my career.
This citizen science project, I think it's going to be our best bet for figuring out actually what's going on with these sprites. And that's exciting to think that might happen in my lifetime. And if it doesn't, I'd be pretty disappointed.